Okay? So these are what are known as the super heavies. So elements beyond uranium. Elements beyond uranium, these are synthetic. These are synthetic. And where are they made? The manufacturing facility, there's 3 places on the planet that have the high energy physics equipment in order to make these. And these are the 3 places. One is Dubna in the former Soviet Union in Russia. One is in Darmstadt in Germany. And the third one is in the United States in Berkeley. These are the 3 places where they have the accelerators and the kinds of reactions. Here's how they were able to make Darmstadtium. They take an atom of lead, accelerate it, and have it collide with an atom of nickel. And if the conditions are right, they will combine, fuse, and form Darmstadtium plus neutron. So these devices, when I was a youngster, were colloquially known as atom smashers because they have the capacity to actually break these and have them reform. And there's various forces that play in the nucleus that will dictate when this will be stable and when it won't be. Yeah, they isolated it, but it decays very quickly on the order of microseconds. Lifetime on the order of microseconds. So you can imagine that's why we don't have the boiling point of Darmstadtium and this electrical conductivity. Right? They've isolated it enough that they can actually say the bare minimum about it. And so we have it. And then just so that you'll be literate in the rest of the periodic table, if you look at the higher ones, this is how you name them. Use these Latin prefixes. So 111 would be un plus un plus un. So 115 is un pentium. And that's why you see these UUP, UUN. So my favorite is 111 because that's unium. So I'm going to be sad when they finally get a name for it. Yeah, there they are. Okay. And when they are named, they're named by suggestion by the scientists who have isolated them. And there's a lot of competition. Obviously, if it's a Russian team that isolates the element, they're going to advocate the name of a Russian scientist or a Russian location or whatnot. Obviously, the work that was done to isolate 110 was done in Germany, and they proposed the name Darmstadt, and hence it's named Darmstadtium. There is a dubnium, and there's also berkelium. And there's all, if you look in the very high numbers, you'll see these nomenclatures. So there's Darmstadtium sitting here. For reading, if you're really curious about some of this early history, I can recommend this book. It's Mendeleyev's Dream. I read it summer before last. It's got a lot, of course, about Mendeleyev, but what's really interesting is the author assumes that the reader hasn't taken 3091, and so the first 3 chapters take you through the history of chemistry, starting with Democritus, and takes you through the Aristotelian theory. After you've had these lectures, it'll be a joy to read. Okay, so now let's go inside the atom. Let's go inside the atom to try to understand what's going on. And this is taken from your book, Table 1.3. And so these are the subatomic particles that we have to contend with. We have the electron. It bears a negative charge in a value of minus 1.6 times 10 to the minus 19 coulombs. This is the SI unit, the Système International unit for electric charge. And it has a mass of 9.11 times 10 to the minus 31 kilograms. The charge compensation comes out of the nucleus with the proton, and it's positive 1.6 times 10 to the minus 19 coulombs. But its mass is 1,800 times that of the electron. The electron is just a little gnat in comparison to the proton. And then there's this third species, the neutron, which has no charge, roughly equal in mass to that of the proton. And so what we do in order to designate the identity of an atom is to do the following. I'm going to let this be, this is the atomic symbol. The atomic symbol which was given by Berzelius. This is the Latin 1 or 2 letter character. And we begin with the proton number. The proton number is in the lower left corner, Z. proton number of protons in the nucleus, which in the neutral atom, this is number of protons in the nucleus, which in a neutral atom is equal to the number of electrons. Now to get to the number of neutrons, what we do is we go up here to the upper left, and this is called the atomic mass. Atomic mass, and it's equal to the sum of the number of protons plus the number of neutrons. So we get at the number of neutrons indirectly because we know the proton number here. This is sum of protons plus neutrons. And we don't put the mass of the electrons because they're so light in comparison. So this will give us the sum that we need. And at some level, we really, there's some redundancy here. So if we want to write sodium, for example, sodium 23, 11. Well, 11 means it's sodium. If you've got 11 protons, it must be sodium. So we could get away with just 23 sodium. And if you wanted to be really, really smart, Alec, you could write sodium like this. You don't need anything here. Okay? Just a suggestion. Now, atoms need not be neutral. They need not be neutral. They can be charge deficient or charge excessive. And so Michael Faraday coined the term ion. Coined the term ion for atoms of net charge. Atoms and other species bearing net charge. So, for example, the positive ions, these are electron deficient. We can't do anything about protons. They're buried in the nucleus, but we can add or subtract electrons. So the positive ions are electron deficient, and these are known as cations. They're known as cations, and you can use mnemonics to try to keep these straight. I see the T as sort of a plus sign. You also know that it comes from the fact that in an electrochemical cell that the cations are those that are reduced. So, you know, from catastrophe, kata is Greek for down, catastrophe is a downturn. So that's the cation. The negative ions, these are electron rich. They have an excess of electrons, and these are known as anions. Anions, all right? It's got the N, which might conjure up negative, or anion and minus both have 5 letters. I don't know how you want to try to keep those straight. But anyways, okay.